First high-level topic we'll discuss in this section will be the wireless location techniques. A little information on wireless location services in general. So the location part of location services is really trying to put a client or a device on a spot in the map, so figuring out where it is. The services part is trying to actually add value to that information. So the services might be running on a server itself. So we might grab all this information, spit it out to a server, and the server is really doing some sort of analytics. So it's watching how people walk through a casino or walk through a retail store, and they can track traffic patterns of all their customers. And from that, they can gather information on how to best lay out their store and where do you want to put your different end caps and product placements so that they maximize their business. Or the application could run on a client itself. So for instance, I'm walking through a mall. I've got a little app running on my smartphone, and when I walk past a restaurant in the mall, all of a sudden I see them next to the restaurant, so the restaurant's specials of the day pop up, or happy hour advertisements, whatever it is. So both services, whether it's client-based, server-based, it all falls under the location services umbrella. So this combination of providing the location information and services around it in the Cisco world is referred to as context-aware services, or CAS for short. Now, on the Cisco side, the location services are really categorized as what's referred to as a near real-time location system, or NRTLS. Near real-time because it takes a couple of measurement cycles to actually put a client on a map. So while it's not 100% real-time, it's very close to it. These services, the CAS services, are provided by the Mobility Services Engine, or MSE for short. Prior to the MSE, it was based off of a server just called a location server. But the MSE, it is historically been a physical appliance. So you just get this 1U rack-mounted server that you put somewhere in your server farm. In newer code, though, they started offering a virtual server. So you could either run it physical, the way it's always been, or you could place it inside an ESX or ESXi farm and run it there. So today we have the choice, but at the time of this exam writing, or based off of the code level of this exam, they only had the physical servers. So here's a list of all the different techniques to know about and understand how they work for location. We kind of start at a real generic level at the top of the list, and as it goes down the list, it gets really more specific, more technologically complex as we go down the list. So we'll kind of start at the basics, and then we'll get into some more real specific and more technical ways of computing location. But before we do that, let's just give you a little bit of background in terms of what you want to know to gauge the location accuracy or the results. So successive location results are measured typically based off of both accuracy and precision, and you might wonder what the difference is. So accuracy, how close to the real position is it? So if you think of a bullseye, a target, how close, to that middle center circle are you getting? That's the accuracy. Now precision is how similar repeated results are to each other. So if I'm very precise, again, think of the target shooting, all of my shots will be in a real tight circle. It doesn't necessarily mean that I'm super accurate, but they're all in a very small range, so that's precision. So in general, accuracy is your main goal, because that's going to get you, I would say, closer to where the client actually is, over time. And then precision really is your margin of error. So the more precise you are, the tighter your circle is. So if I drew that out just real quick, a visual representation might be helpful. So if I have my little target, think about different rings that get bigger. So accuracy is, how close I am to that center target. So if all my shots are pretty much surrounding it, I'm pretty accurate. But if I had my target here, and all my shots were kind of spread around over to the side, that's not accurate. So accuracy, how well am I essentially surrounding the target? Now precision, if all my shots are in this one little area, I'm very precise because, you know, repeated shots are all falling into a very small area. Whereas if I'm imprecise, very spread out. So ideally, we're very accurate, so we're surrounding the center spot there, and I'm very precise, which is shrinking the margin of error. So that's accuracy and precision. All right, now let's actually dig into the topics themselves. First one we'll talk about is cell of origin. This is about the most basic thing you could ever really do. This simply assumes that the client is located near the AP that it's actually associated to. So what's good about this? One, just about any system can do it, because all it really needs to know is, okay, what AP is the client associated to, and where's the AP located? That's where I put my client. So it doesn't take any complex calculations to do. Just about any system could do it. The cons, one, it only works for 802.11 devices because the client actually has to be associated, and then that would be the second one. Just because you're associated to an AP doesn't mean that that's necessarily the closest AP to you. So again, if we go ahead and draw, let's say that I have, you know, a few different APs around here, and my client is right here. Now the closest AP would be this guy. So if I'm associated to that, that's great. But depending on your client, as you're walking around, all of a sudden, you know, we could start associated to this AP here, but as my client moves, my client might move over here, and it might just hang on to that. Depending on client drivers, it's always the client that determines, you know, okay, when do I want to roam, where do I roam to, things like that. So once it's on this AP, it might be prone to just sticking to it until it can't use it anymore, and then at that point it'll roam. So just because it's associated to an AP doesn't necessarily mean it's going to be the actual closest AP to it. With this, accuracy is generally good because if you think of the AP itself as the center point, in general, if you look at the overall floor area, you know, if you're near the AP, you're probably associated to it. So accuracy is generally going to be good, but precision is just going to be horrible because you could be, you know, 40 feet away and still, you know, showing on that AP. So while it's a very simple method to deploy, it's horribly inaccurate, well, horribly imprecise. Pretty accurate, but really very imprecise. A little bit better version of doing this is the modified cell of origin. So rather than just assuming the client is located near the AP it's actually associated to, it's going to put it close to the AP that sees it at the strongest level. So now we're not depending on client drivers, things like that. The APs are just looking at, okay, how loud do I hear this client? And whichever AP hears the client the loudest, it assumes that the client is near that AP. So pros on this one, again, very simple. Slightly more complex than the original cell of origin, but all it has to do is just look at, okay, of all the APs that see this, who sees it the loudest? There's no real complex calculations going on behind it. This can also track non-associated clients, so now if it just sees the client, you know, maybe beaconing or probing, whatever it's going to be, it can track that as well. So the client doesn't even have to be technically associated for this to work, since we're not just assuming it's near the one that it's associated to. Cons on this, precision is still going to be pretty bad. You know, well, it's not quite as bad as it could be with the regular cell of origin. It's downright bad. So accuracy, again, is going to be generally good because it's going to place it closer to the AP that hears it the loudest. So again, decent accuracy, but the precision, again, is just going to be horrible. So not a great method to use. RSS lateration. Now this is a little bit more, again, intelligent way of placing things. It's going to give you better results. So what this does is essentially it's triangulation based on RSSI values. So if you think about what triangulation is, just in case you haven't heard of that. So let's say I have 3 APs. You need 3 APs for triangulation to occur. So the way triangulation works is there's a client somewhere in the middle here. All the APs hear it at a specific RSSI level, and it just assumes, based off the RSSI level, it's a certain distance away. So if we know the approximate distance, we just draw the circumference of the circle with that distance on an AP. If we do this with a couple APs, we get it down to kind of 2 intersection points here. And then we get that third AP in the mix. Ideally, they all kind of intersect at a single focal point. That's where it assumes the client is. So that would be triangulation. Some people call it trilateration. So the pros here, again, like the last one, we can track non-associated clients. And we do generally have an increased both accuracy and precision based off of cell of origin or modified cell of origin methods that we've talked about before. Cons, now we're starting to get into more complex calculations. So it's not just looking at, one RSSI value, it's trying to determine distance based off of RSSI and calculate that across multiple APs to zero in on a single point. So we're probably getting into something where we need an actual server to start to do these calculations with, as opposed to just doing it maybe on the controller itself. And obstacles typically reduce your accuracy here. So if there's more obstacles in between, an AP, let's say there was a big old wall here, a couple walls over here, those obstacles are going to start to reduce your accuracy because it won't necessarily take that into consideration. So with here, accuracy is average, precision is average, so just depending on how many obstacles we have, it's harder to get the accuracy as good as with the other ones, but we get a much better precision, so we're actually probably a lot closer to where the client actually is compared to some of the older methods. Pattern recognition is the next one here. So a step up from the RSS lateration that we just talked about. With this, what we actually do is we take a map and divide it into squares or a grid pattern. And what we do is we do this initial calibration where we walk around and we take lots of measurements in all these different grid areas. And the APs will listen and say, okay, so you tell whatever program you're doing the calibration with, you have your map pulled up and you say, okay, I'm right here, take a measurement. All the APs measure the signal level of that client, and then they know for that area, for that spot, this is what I should see in terms of a signal level on these surrounding APs. Go to another spot, take another measurement. So on each grid, it kind of has these measurements for each grid spot, so that as it takes similar measurements, it looks at, okay, well, what grid best matches these measurements, and I'll place the client there. So kind of a labor-intensive process where you actually have to go through and take a whole ton of measurements across a very large portion of your floor area. But once you've done that, it's actually decently accurate and precise. So the pros here, we're getting even better accuracy, precision over the RSS lateration method. We start taking obstacles into consideration because it's actually taking raw measurements. It's not guessing or anything like that, or assuming path loss based off of obstacles you might be drawing in. Now the cons, it can take a while to do this calibration, especially if you have a very large area. And it doesn't adapt to changing environments. So if you remodel, you got to do another calibration. Or if things change over time, for instance, maybe you're doing this in a warehouse and all of a sudden your stock levels go way up or way down based off of when you did the calibration, that's going to significantly change your results. So as things change, it's going to get less and less accurate and precise until you do another calibration to make up the difference. Now the accuracy here is going to be good, average to good depending on your calibration. Precision is good, and the precision is really going to be based off of how big do you make the grids. So for instance, let's say that I have a floor looks something like this. Now a super imprecise method would be maybe a grid pattern that looked just something like this. So I only have, 12 different grids that something could be placed in. But my calibration would take a whole lot less time. The more precise we want to get means the more grids we have, which means the longer my calibration is going to take. So here I've quartered the grid, the individual square size, but Again, I've made four times the amount of squares, so I'm going to need to take a whole lot more calibration measurements in order to get my precision and accuracy. So the more precise, accurate you get, the longer that calibration process is going to take for you. So the next technique we'll talk about is RF fingerprinting. Now this is what's used by Cisco, so they'll tell you that's the best possible method you could use. There are a couple better methods, but based off of RSSI, this really is one of the best methods you can use. So the way it works, it's a further enhancement of the RSS lateration. So that would be the kind of triangulation or trilateration based off of RSSI values. But we have some enhancements that make it a lot better. So first one, the core of the calculation is really based off of what's referred to as a path loss model. So the path loss being, as the client moves away from an access point, how fast is the RSSI signal dropping? Some environments, if it's got a lot more obstacles, it's going to be a lot faster, although if it's open space, there's really no obstacles, it'll be slower. So it allows it to give it a lot better calculation of distance based off of the measured RSSI values. A few other methods that I use to increase the accuracy and precision. So there's this thing called a minimum mean square error technique. And this is used to minimize the distance between two consecutive location measurements. One of the benefits that this actually can bring is that it can dynamically adjust variables in that location calculation, whether it's the path loss or there's a few other variables in there. It can adjust those over time so that as things change in the environment over time, it can still try to keep that accuracy and precision up. So it actually adapts to a changing environment as opposed to just being static point in time. Another method is the minimum variance estimation, and that kind of helps ignore location aberrations or results that are really different than the previous results were. So if a client is stationary, it assumes the client is staying stationary. Or if a client's moving, it assumes it continues to move in the same direction at the same speed. So if it gets one or two measurements that are really different, all of a sudden it's moving to the left and all of a sudden it bounces way back over here and then it starts moving again, it'll tend to ignore those different measurements that would make it seem like it's really veering off to one side or super speeding up or slowing down. As long as it's only a couple measurements. Obviously, if people truly do turn, it'll catch up and actually start placing them correctly. But most of the time, we tend to get fairly significant differences in RSSI readings, from point A to point B. So it kind of smooths that out and gives you a lot better history of location and overall results. So the pros of this RF fingerprinting method, really it's one of the best location methods we have that's RSSI based. It really beats the pants off of those previous methods. And it works for both associated and non-associated because it is purely RSSI based. The cons, it is computationally complex, so we do need an actual server to do the calculations for us, at least once we start talking about more than any one client at a time. It does not handle a floor which contains significantly different areas very well. So let's say that we had a single floor and one side of the floor was wide open manufacturing where there's no walls, just some machinery over there. And the other half was real dense walled offices. So obviously that path loss is going to be different in the open section compared to the walled office section. So if we had just one floor with that, it can't be accurate everywhere because the path loss model is so different in one area compared to another. A few things though you can do to overcome that. There are tricks and methods you can do. One, if you only care about location over here, you choose the path loss model that most represents the place where you have the most accurate location. The other way you can do is you can just split these two parts of the same floor into separate logical floors, and then now they're doing their own calculations and everything's happy. But it is something you have to overcome when you have significantly different areas in the same building. And it does require a calibration process to get the best results. There's some pre-canned templates that you can use, but if you want to get really good results, you have to do your own calibration. Now, it's not as bad as the calibration that we talked about, where you have to be in every single grid and take measurements there. There's a few different methods, and we'll talk about those as we get into the specific calibration talk. So not as bad as the other ones, but it is a process that you will have to go through. But the good news is accuracy is very good and precision is good as well. So it's a good method to use. Now we're kind of getting out of the RSSI-based location techniques and into some more advanced ones. So the first one we'll talk about is angulation. And it's often referred to either as angle of incidence, AOI, or angle of arrival, AOA, probably more of the angle of arrival part. What this does is it calculates location based off of the direction of where the signal was received. So as long as we have a couple APs that can figure out the direction, they draw a line towards where they think the client is. At some point the lines intersect, that's where the client's located. So if we just draw this out real quick so you can get a visual. So let's say I have my client here. I have a couple APs spread out. They hear the client. This guy knows that the client's in that direction. This guy knows the client's in that direction. So if they just draw a line, ideally the lines intersect where the client's at. So pretty simple in terms of how it calculates it, but more complex in terms of how it has to figure out, the angle that's coming in. Really what this means is that those APs that are hearing the client, they're actually directional APs that are spinning around. So they spin around, and that way, since they are a very directional antenna, they'll hear the client strongest when they're pointed at the client. So based off of that, that's how they can figure out where the client's at. Now, the pros is this is very accurate outdoors. It's really an outdoor-only kind of method, but very accurate. Cons, we need those rotating antennas. Really doesn't work in the Cisco world here. Also doesn't work indoors just because of all the crazy multipath stuff that can go on as signals are bouncing all around, as they tend to do indoors. And it's really not suited for 802.11 networks. So we would never use this really in a Wi-Fi network, but it is a method that's mentioned, so you should know how it works. But accuracy good, precision good, assuming that you're outdoors. Another method is time-based, so time of arrival, sometimes referred to as absolute time of arrival. The way that this works is that both the client and the APs themselves are all synchronized to some sort of a clock. So the client will send a packet of some sort, and it'll actually timestamp the packet with the exact time down to many decimals over in the seconds of when it sent that packet. All of the APs or receivers that hear it will then look at the time, they recorded the time that they received it, compare it to the time stamp in the packet, and so then they know how long it took that packet to get from A to B. And then they assume, RF moves at the speed of light should be, so they can calculate distance based off of how long it took the packet to get from A to B. Then they can do their triangulation or trilateration, so they draw the circle based off of the radius, and wherever those intersect from the 3 or more different APs, that's where the client's at. So there's another method where very accurate outdoors. The cons though, you need both the client and the APs or the receivers to have clocks that are very synchronized with each other. I mean, it has to be super synchronized because 1 millisecond at the speed of light is a very large distance. So both clients and receivers have to be synced up. Doesn't work well indoors, again, and another not suited for 802.11. So really doesn't work in our networks, not something that Cisco supports. Accuracy, precision, very good when you're outdoors, but again, not a method that we could ever use, but something you need to know possibly for the exam. And the last method is time difference of arrival. So very similar to the time of arrival. The difference here is that the client itself doesn't need to be synchronized, doesn't have a synchronized clock. So it's not actually time stamping its packets. So the way it works is the client sends some sort of a packet, and the receivers are all synced up to the same clock. So the receivers, or the APs that receive the signal, they take note of the time that they received it. They send all this information out to some server, and the server will do some sort of complex calculations to figure out, okay, so based off of when all of these APs heard it, it's probably here. So pros, very accurate outdoors. Again, not an indoor type of method. It's not dependent on the client anymore. The client doesn't actually have to have a synchronized clock and timestamp all of its packets or anything. And now we can use that for AO2.11 because our AO2.11 devices don't stamp time. So since we don't rely on that, now we can use this with AO2.11. This is actually supported in the Cisco network, but only for outdoors. The cons, doesn't work well indoors, so we only use this outdoors. Accuracy is very good, precision very good. So in terms of an outdoor method, this is one of the better methods we have to use for accurate outdoor location technologies.